All right, so here we go. So we're doing transformations of exponentials and logs. Okay, so a little review, what a graph of an exponential looks like. Discussed this a little bit on Monday. Now, it kind of depends, right, if we've got a growth or a decay, what it's going to look like, right? If it's a growth, it's going to increase. It's going to head up. If it's a decay, then it's going to do kind of the same thing but going around and coming down. So I'll put both on here for you. So this would be f of x equals a to the x. If we had a growth, let me zoom that in just a little bit so you can see it better once it's done being fuzzy. Maybe a little bit. Okay. And, oh, sorry, it's not a to the x, my bad. It's a times b to the x, right? And what has to be true about b to make that thing a growth? It's got to be greater than 1, right? So this particular graph would be if we've got b bigger than 1. And then we said it's a decay if b is less than 1. So that would look something like this. So we'd have f of x equals a times b to the x. And that's if b is less than 1. Or some kind of a decimal, right? So we're going to have some transformations of those types depending on the base. So you still got to know that, okay? So if I give you an equation and ask you to sketch a graph of it, first thing you got to do is take a look at the b. Is it greater or less than 1? And then that's going to dictate which one of these two you're going to use then, okay? So those are exponentials. A log graph looks very similar to that. It does something kind of like this. So this would be the graph of f of x equals log base b of x. All right. And just like the exponential, there's two different looks to a log depending on the value of b. This is the log graph if b is greater than 1. Okay? And it does the same kind of little flip thing if b is less than 1. And then it does, let's see, so, yeah, it does this. Okay, so that'll be f of x equals log base b of x in the case where b is less than 1. So what I'm going to do with each one of these really quick is I'm going to just put on the same coordinate plane, these two log ones we just did. I'm just going to real lightly with a colored pencil just draw on there what the x is like on the same graph and see if you notice anything. So I'm going to transfer this down onto here real quick. You don't have to, no. Okay, so there's that one. There's that exponential a times b to the x. And then this one, same thing. I'm just going to pull this same exponential down onto here. Okay, anybody notice anything going on there? Yeah? You're close. They're not reflected over x equals 1. Anybody know? Yeah? Y equals x. I think you guys have seen something like that before, right? Potentially. Let's see, where's another color I can steal here? Brown one. Okay, so I'm going to put that line into both of them real quick. Just so maybe that's a little bit more obvious. But that y equals x kind of looks something like that. Okay, so do you see how that's a reflection over that line there? Over here, if I put that in there, looks kind of like that. Okay, reflection over that line. What are we doing when we reflect over y equals x? What were you doing with that before? Do you remember?
No.
Starts with an I. Inverses. Remember when you were graphing inverses, you would reflect it over that y equals x line? Okay. Well, what did we already talk about the relationship between exponentials and logs was? They're what? Inverses, right? So their graphs should look like inverses. Okay, it's doing that same thing. So most people can remember what an exponential looks like, but a lot of people have a hard time remembering what a log graph looks like. And I always tell them, well, remember, it's the inverse of an exponential. So if you reflect it over that y equals x line, there's the log that goes with it. Okay? So both of these are doing that same kind of thing. It's taking that exponential, doing a reflection over the y equals x line, and then there's what the log should look like. Okay? Now, in general, with these log graphs, and this stuff you can actually draw on here, they always go through the same point unless some kind of transformation has been done to them. This point right here should be 1, 0. And same thing over here. I didn't really draw it to scale, but every log, unless it's been moved somehow, is going to go through the point 1, 0. So for this one, it's there. This one, it's there. Okay? So that point, when we start doing these transformations, when we start moving these things around, those I like to consider like your anchor points. So you take that point, and if you're going to move it up, down, left, right, whatever, take that point and move it first, and then see where everything else has to go based on where that point has gone. Okay? And then use that to kind of help you sketch the rest of it. Something else to make note of with these graphs, you guys did talk a little bit about asymptotes in Algebra 2a, correct? You guys remember that or not? Am I wrong in that? Oh, okay. Well, then we can talk a little bit about that right now. An asymptote is an imaginary line that a function approaches but never crosses. Okay? So take a look at this first log graph right here. Do you guys see a vertical line that the log graph gets really close to but never actually crosses over? Okay? It's that y-axis, right? So as it comes down, is it ever actually going to cross the y-axis? No, it just keeps going down, right? So this y-axis, or if you want to give it an equation, technically that's x equals 0, but that x equals 0, that's we call a vertical asymptote because it's getting closer and closer to that line and never actually crossing it. Okay? Do you see how the exponential has a horizontal asymptote? Goes the other way, right? So it gets closer and closer and closer to this line, the x-axis, but never actually crosses it. Okay? Same thing with these guys over here, right? This one is coming up the y-axis, but never crosses it. This one's coming down to the x-axis, but never crosses it. So there's some asymptotes going on over there, too. So as we pick these graphs up and move them around, we're going to pick up those imaginary lines, those asymptotes, and move them, too, with the graph. Okay? And I'll help you with that a little bit when we first get this thing started, what that's going to look like. So before we can jump into that, though, we got to review our transformation rules. Just want to make sure we're all good to go on that. So, and then we'll come back to these graphs and start to put it together. All right, we'll start with some translations, just picking it up and moving it around. So let's say we wanted to move it up and down. So it'd be f of x plus k. So if you have some function and you add a number on the end of it, that moves it up or moves it down depending on if the number is positive or negative. Do you guys remember doing that? So f of x plus 2 would take the graph and move it up 2. F of x minus 2 would take the graph and move it down 2. Okay? So this moves the graph up or down k units. And so the up and down movement, that's the easy one. It's the other one that tends to get people. It's the doing it left and right. Okay, that one's not just added onto the end of the function, that's substituted into the middle of the function. Okay, so you replace x with x minus whatever, x minus h or x minus 1, x minus 5 or whatever. And this moves the function left or right h units. Okay, now here's kind of the sticky wicket on this one. Notice how the up and down was plus k and the left and right is minus h. It's because whatever you see with the horizontal one, it's the opposite. So if it was like x minus 2, what direction would you actually move? To the right, right? If it was a x plus 5, you're actually moving to the left 5, okay? So that's the one that goes the opposite. And then the stretches and shrinks, same kind of a thing. It's the opposite. When it's a left and right type shrink, a horizontal shrink, the vertical stretches and shrinks, those are the normal ones. So if you multiply a function by a number, that's going to stretch or shrink it by a factor of a. Okay, and that's, I guess I should say vertically here, technically at the end there. All right, and this is the one that works the way that you think it should. If a is bigger than 1, stretches it. If a is less than 1, shrinks it down. Okay, you guys all remember that? Doing the stretches and shrinks with that. All right, and then if it's going to be horizontally, then it gets multiplied on the inside. And this is a stretch shrink by b horizontally. But this time, again, it's opposite of what you would expect. So if b is a number bigger than 1, what actually happens there then? That shrinks it down horizontally. And if b is less than 1, it actually stretches it out that way. So be careful with that. So b greater than 1 is a shrink. B less than 1 is a stretch. Okay, so those are all your rules. Let's see if we can take these. To start with, just one at a time, okay? to an equation of an exponential or a log, and then words like, is it a translation, is it a stretch, shrink, by how much, where does it move, all of that. And then can we sketch what the graph should look like too. Okay, so we're going to go to the next page here and try some of that. All right, let's start with this guy. 3 to the x plus 2. So this is a transformation of 3 to the x. Okay, so 3 to the x is kind of like your starting point here. So how has 3 to the x changed to get us to that equation? How has the graph of 3 to the x been changed? Left 2, right, or correct. Okay. How do we know that it is a left 2? Somebody raise your hand so I don't have 6 people answering my question at the same time. Yeah. It's with the x, and what else do you see that lets you know that it's to the left? It's plus, right. You're adding 2, so it's going to move to the left 2. Okay. So let's say we've got f of x equals the natural log of x minus 7. So this one, your starting point would have been natural log x, but what's going on to get you natural log x minus 7? Down 7, right. It's not with the x, right? It's not the natural log of x minus 7. It's the natural log of just x. So you're taking this whole thing and then minus 7, right? So this is a down 7. All right, so there's some translation stuff, what those might look like. Let's try some stretches and shrinks with these real quick, see if you can do those. Let's say we get about 5e to the x. So the starting point for this one would have been e to the x. So what kind of a change happened with e to the x to get us to 5e to the x? Vertical stretch 5, good. You guys are good. Maybe a little too good. All right, let's try this one then. What about that one? 2 to the x over 2.
Horizontal stretch.
It's a horizontal stretch of 1/2. Yeah. Because you would have started with just 2 to the x. Okay? And what happened to the x? It got multiplied by what? 1/2, right? Which is a reciprocal of 2, right? So, yeah, so this thing got stretched horizontally then by a factor of 1/2. Oops. Okay. Now, the way that this is described, this is the way that your book does it, so I did it that same way, but I think calling it a horizontal stretch of 1/2 is a little bit misleading, because technically if it's been stretched out, it's like twice as long as it was, right? So I'd be more apt to say this is a horizontal stretch of 2, because when you look at the graph, it's going to be twice as stretched out as it was. So I'm going to keep doing it like this because I think it's what you're used to. It makes more sense maybe. But when you look at the graph, though, it kind of makes more sense to think of it as like it's twice as stretchy as it was, or twice as pulled out. So it's a horizontal stretch of 2, but, you know, whatever. Not a big deal. Okay. So it seems like you guys are okay with that. There is one thing that we haven't talked about, and I want to see if you guys remember this, if you can tell me what's going on. I didn't write it down as one of your rules earlier, but I want to just quick quiz you here and see if you can tell me what's going on. Let's say we've got log base 3 of negative x. Do you remember what the negatives do? Yeah? Yes, good. Yep. That's a reflection. Anytime you put a negative in there, it's going to be a type of reflection. And when the negative is on x, it's a reflection over the y-axis. Oops. Okay, so that's true of logs and exponentials, right? Doesn't matter. If it's just the x that has the negative, then that's a reflection over the y-axis. And then you guys can probably guess what I'm going to do here now. If we had, let's say, negative 2 to the x, what does putting a negative in front of the whole thing do? Yeah, it's a reflection again, but it's a reflection over the x-axis. All right, so let's try some combos. Do a few of these at the same time. Well, maybe a couple, 2, 3 of them at the same time. See if you can catch on to what's going on. So all right, so if I have a graph of 2 log x minus 3, and these we're gonna draw some little sketches of them too, real quick. So if I've got 2 log x minus 3, what's going on there? Let me just describe. So we got a vertical stretch of 2, and yeah, you would say a horizontal translation of 3, or you can just say goes to the right 3. That's fine.
Please excuse the interruption. We just have a few announcements. Seniors, the deadline for your senior pictures is tomorrow. Please email your senior pictures to Mr. Schoolhouse by the end of the day tomorrow. If you don't submit a picture, your student ID picture will be used in the yearbook. Also, seniors, your names are in the office. Please come check the clipboard next to the clipboard and see Mr. Skipper. On that clipboard is your name. Please make sure everything is spelled correctly and your parents' name. This is for your diploma. Thank you.
All right. So let's draw this thing. So first thing I want to do is sketch the original function. Okay. And if you need to write that out, that's fine. Okay. So without the vertical stretch, without the right 3, our original function, and I'll call it g of x, would have just been log x. Okay? So just a regular log graph. What's the base if I don't write a base in there? 10, right? Common log. If you don't write it, it's actually 10. So is this going to be like a growth type log or a decay type log? Growth. So it's going to look like this. And it's going to go through the point 1, 0, like we talked about. That's kind of that little anchor point we're going to use. Okay, so a vertical stretch of 2 Okay, that's not going to move this point. It's still going to be on there, but all it's going to do is it's just going to look a little more stretchy. It's going to be a little skinnier. So after that vertical stretch of 2, it's going to look maybe something kind of like this. And then I want to take that and shift it to the right 3. Okay? So where is that anchor point going to be now if I shift it to the right 3? 4, 0, right. Okay, and it's still going to have that same kind of stretchy look like the orange one was that I drew. So something kind of like that. Remember we talked about asymptote? This has a vertical asymptote, that is the y-axis. That asymptote has to come along when we move it. So where is that vertical asymptote going to be now? It used to be right on the y-axis. So it's going to be moved over to 3. Yeah. So it comes down and intersects just 3. So that's going to be, let's say here's 3. And we make a little dotted line to show where it is. If it's not an axis, we got to have a way to show it so that we don't confuse it with everything else. So we do a little dotted line. So that vertical asymptote is over at 3, and then it comes up, passes through the point 4, 0, and it's a little stretchier looking. Okay? So let's do one more together. Then I'm going to have you guys bust out your journals and practice this a little bit on your own. So, all right. We'll do an exponential one this time. So let's do... negative e to the x plus 1. So what's happening on this one? Reflection over the x. So, okay, so yes, it is a reflection over the x-axis because the negative's in front of the whole thing. And yeah, it's to the left because it's on the plus 1 is with the x, it's not with the whole function. So this goes to the left 1. All right, and our home base for this one would have been what? Yeah, it's just, yeah, okay. So without any of the transformational stuff going on, it's just e to the x. So we want to sketch e to the x, do this stuff to it kind of like we did the last one. All right, now is e to the x a growth or a decay? It's a growth. So I have to draw an exponential graph, make it look like a growth. So that's going to be like this. All right, so quick question for you. Where does that cross the y-axis?
1.
At 1, right? Usually you would have like a times b to the x, but there's no a multiplied in front here, but that would just be a 1 then. Okay, so if you don't see anything in front of the exponential, it's always going to go through the point 1. So this one's got another little anchor point on it. It's 0, 1. Okay, so we're going to have to figure out what happens to that little point 0, 1 when we move things around. And it's got a horizontal asymptote, right? Right on the x-axis. So we've got to figure out what happens to that too. Okay, so first things first, reflection over the x-axis. So let's sketch that out. I'm going to do that in orange here. So it would look something kind of like that. Where did that little point 0, 1 go? So where's what are the coordinates of that now? Careful, what are the coordinates? Oh. Don't jump ahead. What is the point right now? 0, negative 1. Okay. So that's after the reflection, and then we need to take that thing and scoot it to the left 1 unit. Okay, so where's the little anchor point going to be now? Negative 1, negative 1. Yeah. So maybe, I don't know, like somewhere over here now. All my coordinates are kind of getting smashed together here. But, anywho, it's going to look something like that. Okay. What happened to the horizontal asymptote? Stayed the same, right? Nothing happened to it. Once I reflected it over the axis, it's still in the same place. And then I scooted it to the left, and then that doesn't change where that thing is. Now, if I had moved it up or down, that would change it, right? That asymptote would have to come along up and down, however far it got moved. But because I shifted it to the left, nothing happened to that, and it's just stays where it is. Okay, so that little brown graph there would be the final one for this one then. Okay. All right, so let's give this a little bit of practice with our journals here. So turn to page, I don't remember, 100 and something. 173. 173. All right. Here's what we're going to do. Everybody, I'm going to pass around the colored pencils. Everybody's going to take 2 colored pencils because you have to graph the original function and what the function looks like after all the transformation stuff has happened. Okay? So pick your 2 favorite colors and then each a try and see how you do.